Now, let us study Earth's gravitational acceleration. The Earth exerts gravitational force on the objects near it. According to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, the gravitational force due to the Earth on a body results in its acceleration. This is called acceleration due to gravity and it is denoted by g. Acceleration is a vector, as the gravitational force on any object due to the Earth is directed towards the center of the Earth. The direction of the acceleration due to gravity is also directed towards the center of the Earth, that is, vertically downwards. Think about it, children. What would happen if there were no gravity? There would be no gravitational attraction between any two particles and hence no formation of solar system, galaxies, etc. What would happen if the value of g was twice as large? The gravitational force between any two particles would become double. Also, the value of g becomes double. Now, let's learn value of g on the surface of the Earth. Value of g on the surface of the Earth. We can calculate the value of g by using Newton's universal law of gravitation for an object of mass m situated at a distance r from the center of the Earth. The law of gravitation gives F is equal to gmm upon r square. M is the mass of the Earth, so F is equals to mg. From these two equations, mg is equal to g capital M small m upon r square. G is equal to gm upon r square. If the object is situated on the surface of the Earth, r, that is capital R, is the radius of the Earth. Thus, the value of g on the surface of the Earth is g is equal to capital Gm upon capital R square. Thus, unit of g in SI unit is meter per second square. The mass and the radius of the Earth are 6 into 10 raised to 24 kg and 6.4 into 10 raised to 6 meters respectively. Using these in equation number 6, we get g is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 upon 6.4 into 10 raised to 6 the whole square, which after calculating gives 9.77 meter per second square. Let this be equation number 7. This acceleration depends only on the mass m and radius r of the Earth, and so the acceleration due to gravity at a given point on the Earth is the same for all the objects. It does not depend on the properties of the object. Can you tell, children, what would be the value of g on the surface of the Earth if its mass was twice as large and its radius half of what it is now? G is equal to gm upon r square. Therefore, small g is equals to capital Gm1 upon capital R1 square and G2 is equals to Gm2 upon R2 square. Therefore, G2 upon G1 is equal to M2 upon M1 into R1 upon R2 square. G2 is equal to G1 is equals to M2 upon M1 into R1 upon R2 the whole square. That is G1 is equals to 2 into 2 the whole square. So therefore M2 is equals to 2M1 and therefore R2 is equals to R1 upon R2. Therefore G2 is equal to 8G1. Thus the value of G on the surface of the earth would be 8 times the present value. Got it? Now let's study variations in value of G. First, change along the surface of the earth. Will the value of G be same everywhere on the surface of the earth? The answer is no. The reason is that the shape of the earth is not exactly spherical, and so the distance of a point on the surface of the earth from its center differs somewhat from place to place. Due to its rotation, the earth bulges at the equator and is flatter at the pole. Its radius is largest at the equator and smallest at the poles. The value of G is thus highest, that is 9.832 meter per second square at the poles and decreases slowly with the decreasing latitude. It is lowest 9.78 meter per second square at the equator. Change with the height. As we go above the Earth's surface, the value of R in equation 5 increases and the value of G decreases. However, the decrease is rather smaller for heights, which are small in comparison to the Earth's radius. For example, remember that the radius of the Earth is 6,400 kilometers. If an aeroplane is flying at a height of 10 kilometers above the surface of the Earth, its distance from the Earth's surface changes from 6,400 kilometers to 6,410 kilometers, and the change in the value of G is due to its negligible. On the other hand, when we consider an artificial satellite orbiting the Earth, we have to take into account the change in the value of G due to large change in the distance of the satellite from the center of the Earth. Some typical heights and the values of G at these heights are given in the table. Place surface of the Earth, that is average. Height is 0 kilometers and G is 9.8 meter per second square. Place Mount Everest. Height 8.8 and G is also 9.8. Place maximum height reached by man-made balloon. Height 36.6 and G is equal to 9.77. Place height of a tropical weather satellite. Height 400 kilometers and G is 8.7 meter per second square. Place height of communication satellite. Height is 35,700 and G is 0.0 2 to 5. Change with the depth. The value of G also changes if we go inside the earth. The value of R in equation 5 decreases, and one would think that the value of G should increase as per the formula. However, the part of the earth which contributes towards the gravitational force felt by the object also decreases, which means that the value of m to be used in equation 5 also decreases. As a combined result of change in r and m, the value of g decreases as we go deep inside the earth. Now think about it, children. Will the direction of the gravitational force change as we go inside the earth? No. What will be the value of G at the center of the earth? 0. Every planet and satellite has a different mass and radius. Hence, according to equation 6, the values of G on their surfaces are different. On the moon, it is 1/6 of the value of the earth. As a result, using the same amount of force, we can jump 6 times higher on the moon as compared to that on the earth. So now let's study mass and weight. Mass. Mass is the amount of matter present in the object. The SI unit of mass is kg. Mass is a scalar quantity. Its value is same everywhere. Its value does not change even when we go to another planet. According to Newton's first law, it is the measure of the inertia of an object. Higher the mass, higher is the inertia. Weight. The weight of an object is defined as the force with which the earth attracts the object. The force on an object of mass m on the surface of the earth can be written using equation 4. Therefore, weight, that is W, is equals to F is equals to mg, and G is equals to Gm upon R square. Weight being a force, its SI unit is Newton. Also, the weight being a force is a vector quantity and its direction is towards the center of the earth. As the value of G is not same everywhere, the weight of an object changes from place to place, though its mass is a constant everywhere. Now let's study some solved examples. Example number 1. If a person weighs 750 N on earth, how much would be his weight on the moon given that moon's mass is 1 upon 81 of that of the earth and its radius is 1 upon 3.7 of that of the earth? Let's look at the solution. Weight on earth is 750 N. Ratio of mass of the earth me to the mass of the moon mm is me upon mm is equals to 81. Ratio of the radius of the earth re to the radius of the moon rm is re upon rm is equals to 3.7. Let the mass of the person be m kg. Weight on the earth mg is 750 is equals to mg me upon re square. Therefore, m is equals to 750 re square upon gme. Let this be equation 1. Weight on moon is equals to mgmm upon rm square. Using equation 1, we get 750 re square upon gme into gmm upon rm square is equals to 750 re square upon rm square multiplied by mm upon me. We get 750 multiplied by 3.7 the whole square into 1 upon 81. The answer is 126.8 n. The weight on the moon is nearly 1/6 of the weight on the earth. We can write the weight on the moon as mgm, where gm is the acceleration due to gravity on the moon. Thus, gm is 1/6 of the g on the earth. Now let's learn free fall. Try this, children. Take a small stone. Hold it in your hand. Which force are acting on the stone? Now release the stone. What do you observe? What are the forces acting on the stone after you release it? The forces are acting on that small stone are the force exerted by the person holding it, the force exerted by the air, and the earth's gravitational force. After releasing the stone, it falls on the ground. The force acting on the stone after releasing it are the force exerted by the air and earth's gravitational force. We know that the force of gravity due to the earth acts on each and every object. When we were holding the stone in our hand, the stone was experiencing this force. But it was balanced by the force that we were applying on it in the opposite direction. As a result, the stone remained at rest. Once we release the stone from our hands, the only force that acts on it is the gravitational force of the earth, and the stone falls down under its influence. Whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. Thus, the released stone is in a free fall. In a free fall, the initial velocity of the object is 0 and goes on increasing due to the acceleration due to the gravity of the earth. During free fall, the frictional force due to air opposes the motion of the object, and a buoyant force also acts on the object. Thus, true free fall is possible only in vacuum. For a freely falling object, the velocity on reaching the earth and the time taken for it can be calculated by using Newton's equations of motion. For free fall, the initial velocity u is 0 and acceleration a is g. Thus, we can write the equation as v is equals to gt. S is equals to 1 upon 2 gt square. So, v square is equals to 2gs. For calculating the motion of an object thrown upwards, acceleration is negative. That is in a direction opposite to the velocity and is taken to be negative g. The magnitude of g is the same, but the velocity of the object decreases because of this negative acceleration. The moon and the artificial satellites are moving only under the influence of the gravitational field of the earth, thus they are in free fall. Now let's study some solved examples. Example 1. An iron ball of mass 3 kg is released from a height of 125 meter and falls freely to the ground. Assuming that the value of g is 10 meter per second square, calculate the time taken by the ball to reach the ground, velocity of the ball on reaching the ground, and the height of the ball at half the time it takes to reach the ground. Given m is equals to 3 kg. Distance travelled by the ball s is 125 meter. Initial velocity of ball, that is u, is 0 and acceleration a equals to g is 10 meter per second square. Now according to Newton's second equation of motion, S is equals to ut plus 1 upon 2 at square. Therefore, 125 is equals to 0t plus 1 upon 2 into 10 into t square is equals to 5t square, where t square is equals to 125 upon 5 is 25. Therefore, t is equals to 5 seconds. The ball takes 5 seconds to reach the ground. According to Newton's first equation of motion, final velocity v is equals to u plus at is equals to 0 plus 10 into 5, which is 50 meter per second. So the velocity of the ball on reaching the ground is 50 meter per second. And half time, that is t, is equals to 5 upon 2, which is 2.5 seconds. Ball's height at this time, that is equals to s. According to Newton's second equation, s is equals to ut plus 1 upon 2 at square. S is equals to 0 plus 1 upon 2 into 10 into 2.5 the whole square, which is equals to 31.25 m. Thus, the height of the ball at half the time is 125 minus 31.25, which is 93.75 meters. Example 2. A tennis ball is thrown up and reaches a height of 4.05 meter before coming down. What was its initial velocity? How much total time will it take to come down? Assume g is equals to 10 meter per second square. Now solution. Given for the upward motion of the ball, the final velocity of ball is v is equals to 0. Distance travelled by the ball is 4.05 meter. Acceleration a is equals to minus g is equals to minus 10 meter per second square. Using Newton's third equation of motion, v square is equals to u square plus 2as. 0 is equals to u square plus 2 into minus 10 into 4.05. Therefore, u square is equals to 81 and u will be equal to 9 meter per second. The initial velocity of ball is 9 meter per second. Now let us consider the downward motion of the ball. Suppose the ball takes t seconds to come down. Now the initial velocity of the ball is 0. That is u is equals to 0. So distance travelled by the ball on reaching the ground is 4.05 meter. As the velocity and acceleration are in the same direction, A is equals to G is equals to 10 meter per second. According to Newton's second equation of motion, S is equals to ut plus 1 upon 2 at square. 4.05 is equals to 0 plus 1 upon 2 into 10 into t square. So t square is equals to 4.05 upon 5, which is equal to 0.81. Therefore, t is equals to 0.9 seconds. The ball will take 0.9 seconds to reach the ground. It will be the same time to go up. Thus, the total time taken is 2 multiplied by 0.9, which is 1.8 seconds. Now children, use your brain power. According to Newton's law of gravitation, Earth's gravitational force is higher on the object of larger mass. Why doesn't that object fall down with higher velocity as compared to an object with the lower mass? According to Newton's law of gravitation, the Earth's gravitational force is higher on an object of larger mass. But that object doesn't fall down with higher velocity as compared to an object with lower mass, because F is equals to ma and F is equals to gmm upon r square. Therefore, acceleration A is equals to gm upon r square. This is independent of the mass m of the object. Hence, an object of a larger mass and an object of a lower mass falls down with the same speed. Now, let's learn gravitational potential energy. We have studied potential energy in last standard. The energy stored in an object because of its position or state is called potential energy. This energy is relative and increases as we go to a greater height from the surface of the earth. We had assumed that the potential energy of an object of mass m at a height h from the ground is mgh, and on the ground it is 0. When h is small compared to the radius r of the earth, we can assume g to be constant and can use the above formula mgh. But for large values of h, the value of g decreases with the increase in h. For an object at infinite distance from the earth, the value of g is 0 and Earth's gravitational force does not act on the object. So it is more appropriate to assume the value of potential energy to be 0 there. Thus, For smaller distances, that is heights, the potential energy is less than 0. That is, it is negative. When an object is at a height h from the surface of the earth, its potential energy is minus gmm upon r plus h. Here m and r are Earth's mass and radius respectively. Escape velocity. We have seen that when a ball is thrown upward, its velocity decreases because of gravitation of the earth. The velocity becomes 0 after reaching a certain height, and after that the ball starts falling down. Its maximum height depends on its initial velocity. According to Newton's third equation of motion is v square is equals to u square plus 2as, where v is the final velocity of the ball, 0, and a is minus g. Therefore, 0 is equals to u square plus 2 into minus gs, and the maximum height of the ball s is minus u square upon 2g. Thus, higher the initial velocity u, the larger is the height reached by the ball. The reason for this is that the higher the initial velocity, the ball will oppose the gravity of the earth more, and larger will be the height to which it can reach. We have seen above that the value of g keeps decreasing as we go higher above the surface of the earth. Thus, the force pulling the ball downward decreases as the ball goes up. If we keep increasing the initial velocity of the ball, it will reach larger and larger heights, and above a particular value of initial velocity of the ball is able to overcome the downward pull by the earth and can escape the earth forever and will not fall back on the earth. This velocity is called escape velocity. We can determine its value by using the law of conservation of energy as follows. An object going vertically upwards from the surface of the earth, having an initial velocity equal to the escape velocity, escapes the gravitational force of the earth. The force of gravity being inversely proportional to the square of the distance becomes 0 only at infinite distance from the earth. This means that for the object to be free from the gravity of the earth, it has to reach infinite distance from the earth. That is, the object will come to rest at infinite distance and will stay there. For an object of mass m on the surface of earth, kinetic energy is 1 upon 2 mv square, that is velocity of escape, and potential energy is minus gmm upon r. So, total energy is equals to E1, that is kinetic energy, plus potential energy, is equals to 1 upon 2 mv escape square minus gmm upon r. At infinite distance from the earth, kinetic energy is equals to 0. Potential energy is minus gmm is equals to 0 upon infinity is equals to 0. Total energy E2 is equals to kinetic energy plus potential energy is equals to 0. From the principle of conservation of energy, E1 is equals to E2. So 1 upon 2 mv square minus gmm upon r is equals to 0. So v square is equals to 2gm upon r. Escape velocity is square root of 2gm upon r is equals to square root of 2gr, which is equal to square root of 2 into 9.8 into 6.4 into 10 raised to 6, which after calculation gives 11.2 kilometer per second. The spacecraft which are sent to the moon or other planets have to have their initial velocity larger than the escape velocity, so that they can overcome Earth's gravitational attraction and can travel to these objects. Let's study solved examples. Example number 1. Calculate the escape velocity on the surface of the moon given the mass and radius of the moon to be 7.34 into 10 raised to 22 kilogram and 1.74 into 10 raised to 6 meter respectively. The solution. Given G is equals to 6.67 into 10 raised to minus 11 nm square per kg square. Mass of the moon is m, that is 7.34 into 10 raised to 22 kg, and radius of the moon r is equals to 1.74 into 10 raised to 6 meter. Escape velocity is equals to v escape is equals to square root of 2gm upon r, which is equals to square root of 2 into 6.67 into 10 raised to minus 11 into 7.34 into 10 raised to 22 the whole upon 1.74 into 10 raised to 6, which gives us 2.37 kilometers per second. Therefore, escape velocity on the moon is 2.37 kilometers per second. So children, it was a long lesson, right? So, please watch the video attentively and please go through the lesson. That means read the lesson. So, with this, we have come to an end of today's session. We shall see you in the next video with a new lesson. Till then, take care children. Thank you very much.